This is my video lab report for Lab 5, where I analyzed a collision between a motorbike and a car. The collision I analyzed was from the first problem for the Spring Test 4, under one of our old tests, under our resources in T-Square. To explain what's going on in this situation, a car and a motorbike collide at constant speeds in a maximally inelastic collision, that is to say, they essentially become one mass. Then I broke this up into two different distinctions, one pre-collision and one post-collision. After the collision, the combined mass is slowed to a stop by friction. So the questions we're asked here is, what is the change of internal energy of the car and bike from the collision? And what is the change in energy of the combined mass as it slows down? Now, in order to analyze this collision and answer some of these questions, we use our momentum principle and our energy principle, which we have learned previously in this semester. We have two different F-net equations here because we have, like I said earlier, our analysis split into two different sections. So for the F-net for the first one is our top equation, and then the F-net for the post-collision is our third F-net equation, as well as our different equations for our change in energy. And just a quick note here, I used a chart from Engineer's Toolbox on the internet to find the static frictional coefficient for a dry tire on a dry road. So we're assuming that our collision happens on a dry, sunny day. So to better explain this pre-collision and post-collision separation in our analysis, the pre-collision starts with the car and the motorbike as our system. And they're two separate entities in our system which collide into one entity in our system. There's no work done in this collision, in this part of the collision, because that net force is equal to zero, with the net force, or with the force of the engine plus the frictional force canceling each other out. Whereas post-collision starts instantly after the collision, so we're looking at one mass. The net force here is acting in the negative direction of the mass's velocity because it's only the friction force is the only force acting on it, so therefore the friction force is the net force here. Using these equations that we previously discussed, as well as our observation of motion, we can calculate the delta K for the pre-collision, which, because there's no work done, the change in kinetic energy also equals a change in internal energy, which is a change of thermal or deformation of the objects in our system. Now, post-collision, it's led to believe that the delta K is the only change in energy occurring here. However, we can see after calculating the work, because there is a net force here that does not equal zero, that occurs over some distance, we can calculate our work, which we set equal to our change in kinetic energy, and we find that there is indeed a difference where it is found to be in the change of internal energy. And having a positive change in internal energy makes sense here because we have a negative change in kinetic energy. In order to have a better understanding, let's look at a physical model created in Python of our collision, where here the red ball equals the motorbike and the blue ball equals the car, and the black is the combined mass. Let's watch what exactly we're going to analyze so we can have a better understanding of which interaction we're analyzing here. So just the car and the motorcycle colliding into one solid object. After breaking it down, this analysis is fairly simple. Our F-net is zero because the force from the engine and the friction force equal one another. Our momentum principle doesn't really matter in this case because the F-net is zero, so there's no real change in velocity. However, there's a change in position, which we use the momentum principle to calculate. The equation for the change in kinetic energy is seen at the bottom, however, it is typed in Python code, so it does look a little funky. But it gets the job done, and we find the change in kinetic energy, which in turn equals the negative change of internal energy because the work is zero. Since the work is zero, we can just move this delta K to the side of the equation and obviously set the negative of that to the change in internal energy. Once again, let's take a quick look at what's happening here so we can understand which part of the interaction we're examining. We see that the black circle being the total mass of the car and the motorbike as moving after the collision. Since we're starting where the other portion of our analysis left off, we use the final velocity for that as our initial velocity for this portion of our analysis. Here the momentum principle's equation for velocity does come into play because F-net is not zero, so there is a change in velocity, which is caused by the friction force, which will eventually lead our velocity to equal zero. Using the same equation for delta K that we used in our first portion of the analysis, we set the work equal to delta K and find a small discrepancy. However, that discrepancy can be accounted for as a positive change in internal energy. Since there's a negative change in delta K, this makes sense. A loss of kinetic energy would, in turn, reveal a gain in internal energy or thermal energy. Now, this portion of our analysis is actually an analysis of a prediction of our collision because we're not given this data in our problem. Ergo, we predict our change in position by our change in velocity, which we in turn use to predict our changes in energy and our work done on our system. Alright folks, thanks for watching.